So what we were doing the last 2 days was finding the derivative of a function at a certain point, or in other words, finding the slope at one particular point. What we're going to be doing today is coming up with an actual derivative function, one that represents the slope at any point. So when we do this, what we'll come up with is a function, an equation, that represents the slope at any point, so you could just plug in a particular value of x once you come up with this function. So we've seen the formula for the derivative before, but this time we are doing with respect to any variable x instead of one particular value of x equals a. So it's the same sort of setup here. Remember, f prime represents the derivative, but this time it's f prime of x, one particular value of x that we haven't yet plugged in. So we've got the limit as h approaches 0, because remember at the very end of this, at the 4-step process, we take the limit as h approaches 0 because we want to shrink that interval down to nothing. And then we've got f of x plus h minus f of x over h. So notice it's almost identical to the formula that we've been using for the last 2 days. The only difference is we've got an x instead of an a. X will stay a variable where a gets replaced with a constant, which is one particular value of x. And then again it says provided that the limit exists. We'll be talking in the next couple days about when the limit doesn't exist and what that looks like and what happens in those cases. So says the domain of f prime may be smaller than the domain of f, or in other words, even if you're looking at a normal function f, it might be, it might exist everywhere, it might be continuous everywhere, but every point might not necessarily have a derivative. So if the derivative exists, we say that f is differentiable. We say that f is differentiable at x. So what that means is that we're able to take the derivative of it. And when you say something's differentiable, that means it's differentiable at every single point in their domain. So you can talk about being differentiable at a point, or you can talk about being differentiable all the time, which means it's always differentiable, just like a continuous function is always continuous. Okay, so this first example we're going to look at, we are finding the derivative of, so that's what I wrote, both notations there. When you say to differentiate, that means find the derivative of something. We want to find the derivative of this function. So notice, again, we're not looking at a particular point. We're looking to find a formula that represents the derivative for any value of x that we might want to plug in. So we still do the exact same 4-step process. So step number 1, we find f of, this time it's just going to be an x plus h. Instead of plugging in 2 plus h or negative 1 plus h, we're just plugging in a generic x. But the process works the same. Oops, saw that 4, sorry. Okay, so we simplify this up. So this is going to be 2, and then we FOIL this out, and we get x squared plus 2xh plus h squared. Distribute the negative 3, and then we've got plus 4. Oops. Okay, so we simplify this up one more time. So we are going to end up with a 2x squared, a 4xh, a 2h squared, and then none of these terms have changed. So we have, 6 different terms here? None of them are like terms, and none of them can be combined up. So the next thing we do is we take this crazy thing that we just got from step 1, so all of that by plugging in the x plus h, and then we subtract f of x. So what happens? We've got a 2x squared that will cancel out, we've got a negative 3x that will cancel out, and we've got a 4 that will cancel out. So remember, at the end of step 2, every single term that you have should contain a factor of h. So we're down to just 3 terms, and they do all have a factor of h. Step 3 is to take what we left off with in step 2, where everything had a factor of h, and we are supposed to divide it by h. And that way, when we leave off with everything having a factor of h in step 2, once we divide by h, we'll knock off all those factors of h and it'll simplify down really nicely. So this ends up with a 4x plus 2h minus 3. So again, remember what this represents. This represents the slope of the secant line between x and x plus h. But we're not looking for a secant line, we're hoping to get a tangent line. So instead of going from x to x plus h, we just want the derivative at x. So we're hoping that the h will just shrink down to 0. So that's always the last step, is we take the limit of that expression that we just found as h approaches 0. And if we did everything correctly up to this point, we should just be able to directly substitute in a 0 for the h. So we end up with 4x minus 3. So that is the derivative, and I guess we should write f prime of x equals 4x minus 3. So what this means is that if I were to plug in any x value into this function right here, it would tell me what the slope is on this graph. So for example, if I wanted to know the slope of this graph at x equals 1, I just plug in x equals 1 to this function and I get 1. So let me show you. So here's the 2x squared minus 3x plus 4. So if we graph this parabola, looks like this. So again, if I wanted to know the slope at x equals 1, I plug the 1 into my derivative function, I get 1, and you can see at 1, sure, a slope of 1 looks pretty feasible, but if you plug in anything to the left over here, say we plug in like a 0 for instance, if you plug in 0 for x, you get negative 3, and that looks about right. If we look at 0, definitely got a negative slope. Negative 3 looks like it could be about right. So you'll notice the dividing line here is when x equals 3/4. So when x equals 3/4, supposedly the slope is 0, and that's actually this low point on the graph right here. So my slopes go from being negative to 0, and then they're positive after that. And that's because this expression that I'm pointing at, it's negative if you plug in something smaller than 3/4. It's positive if you plug in something bigger than 3/4. So that function, again, represents the slope for any value of x that you could plug in. So we're going to do the exact same thing with this next one. Differentiate this function. We've got 2 of them coming up, actually. So same 4 steps. Step number 1, we want to find g of x plus h. So that is 1 over 1 minus, now make sure you're doing minus x, so we do minus x minus h, because you're supposed to be subtracting this entire quantity. Now this, there's not really anything you can do to simplify, so let's jump right to step 2. We take our expression from step 1, and then we subtract the original function, so 1 over 1 minus x. Now we remember how fun these are. So what we're going to do with these is we need to get a common denominator. So this one you're going to multiply top and bottom by 1 minus x. This one you're going to multiply top and bottom by 1 minus x minus h. And we are going to get a lovely common denominator. So our beautiful, beautiful denominator is the quantity 1 minus x minus h times the quantity 1 minus x. So you'll notice here, I'm just multiplying by 1. So this numerator is just going to be the quantity 1 minus x. And then again here, just multiplying by 1. So this is going to be the quantity 1 minus x minus h. So the 1's will cancel. We'll have 1 minus 1. Those will cancel. We'll have negative x minus negative x. Those will cancel. And then we have nothing left over here minus a negative h. So that ends up being a positive h in the numerator. So before we move on to step 3, we need to make sure that every term has a factor of h. This, remember, is only one term. The rational expressions are tricky, and it does in fact have a factor of h. So step 3 is to divide by h. But remember, when I've got one of these fancy expressions like this, instead of dividing by h, I'm going to multiply by 1 over h, which of course means that these will cancel out. And then my 4th step is to take the limit as h approaches 0 of that expression that I just ended up with after step 3. So again, I can go for direct substitution. So if I sub in a 0 for the h, this term will be gone, and then notice I've got 2 exact copies of 1 minus x. So I'll have 1 over, and this will be 1 minus x quantity squared. So that is my derivative function f prime. So same exact thing as I just talked about in example number 1. If I wanted to know the slope of this function at any given point, I would just plug it in right here. Now notice something about this expression. This is always going to be positive, because of course 1 is positive, and then no matter what I plug in here, it's going to be positive. So I want to talk about 2 things here. First of all, what I just said, that the slope should always be positive if I look back at this. And then also notice that if I plug in 1, this function would be undefined, which means the derivative would be undefined. So let's look at the original function, see if we can get that derivative to make sense for us. So there's our graph. Notice at 1 there's no function values, there's definitely no derivative, but what I mentioned about the derivative, no matter what I plug in here for x, I'm going to get something that's always positive, which means my slope is always positive, which you can tell here. I got a positive slope, my function's increasing, positive slope, my function's increasing. The larger the value of x that I plug in, or the more negative the value of x I plug in, the smaller that derivative is going to be, which hopefully you can see by looking at this fraction. All right, another one of these. We've got the square root ones now. So hopefully you're getting pretty familiar with what we do when you come across, a polynomial versus a rational versus a radical, things like that. So when I plug in x plus h, again, there's not really anything that I do to simplify in this very first step. All I do is I replace the x with an x plus h. So my second step is where things get a little crazy. I take my first step, and then I subtract my original function, which is my original h of x, so the square root of x plus 3. Now we've seen these radical functions a couple times before. Remember what you do is you multiply top and bottom by the conjugate of this ridiculous expression here. So this is going to get gross, but remember we're going to take this thing, picture it as being over 1. So we do plus root x plus 3, and then over the exact same thing. So even though this looks absolutely absurd, very complicated, remember, if you look at the pieces, it's really just a fancy one. If I multiply the numerator and denominator by the same thing, all I'm multiplying by is 1. So let's simplify this up. So when I FOIL out the numerator, this quantity times this quantity, the square roots cancel, and all I have is an x plus h plus 3. And then the outside terms and inside terms cancel, just like they have with every conjugate we've used, and then minus this last quantity here. So minus the quantity of x plus 3, no square root this time. So remember, root x plus 3 times root x plus 3 just gives me the quantity x plus 3. So my denominator is this gorgeous radical conjugate down here. And one last thing to do, we've got the x's, x minus x will cancel out. 3 minus 3 will cancel out, so I'm left with just an h in the numerator. And so I'll say this again, the entire point of doing that was because at the end of step 2, every factor that I have is supposed to have, every term that I have is supposed to have a factor of h. So even though this is a crazy, rational, and radical expression, it's only one term, and it does have a factor of h. So step 3 is to take that beautiful term, and divide it by h, which means we're going to multiply by 1 over h. Of course, we're expecting the h's to cancel. So here's what I'm left with. So remember again what this represents. This is the slope of the secant line between x plus h and x. But I want the secant line to become a tangent line, which means I want h to approach 0. So for my final step, I take the limit as h approaches 0. Thank goodness, this is the last time I have to write this expression down. So you'll notice something very similar to what we just did in the one up above. When this h cancels, these two terms are exactly the same. The one up above, they were multiplied. This one, they're added. So when I have root x plus 3 plus root x plus 3, what that means is that I have 2 of them. So I have 2 root x plus 3 in the denominator. And that is my derivative, f prime. So same exact thing as example 1, same exact thing as example 2. If I wanted to know what the slope of this function was at any given value, all I do is plug in that x value in here and it tells me what the slope is. Okay, so some notation. We've talked about f prime. There's a bunch of different ways that we can do notation. You could see y prime. So like, f of x and y are kind of, you can swap one out for the other. So instead of f prime, you could see y, which we read as y prime, just like we read f prime of x. You could see this. That's a dy in the numerator, a dx in the denominator. This is read as, we literally read dy by dx. And so what this represents, this is the derivative of y with respect to x. So again, the derivative of y with respect to x. Or we could see this. So if you want to show like taking the derivative of both sides, you put the function in parentheses and then d by dx, this represents taking the derivative. So this is d by dx of f of x, or in other words, the derivative with respect to x of f of x. And that's where you'd actually plug the function in. I'm just writing a generic f of x right now, but you would actually plug the function in there. All right, our last little bit is about one-sided derivatives, very similar to the idea of one-sided limits, because the derivative definition that we gave is actually a limit. So we've got this little note here: a function is differentiable on a closed interval if it has a derivative at every interior point. Okay, so again, if it's differentiable if it has a derivative at every interior point on the interval. Now we say interior point because that doesn't include A and it doesn't include B, and that's because you can't talk about being differentiable at an endpoint, because you need to talk about what's happening from the left and what's happening from the right. So at A, for example, you would have no idea what's happening from the left, and at B you would have no idea what's happening from the right. So we can't talk about being differentiable at A or at B. So if these limits exist, we can have a right-hand derivative and a left-hand derivative. So the limit as h approaches 0 from the right, and here we're going to go back to A. This is the right-hand derivative. At x equals A. So if we were looking at like x equals 3, for instance, this would be going from 3 to 3.1, 3 to 3.01, 3 to 3.001. So very similar to a right-hand limit. We're coming in from just above the value of x that we're interested in. So that's the right-hand derivative. And then we can do the left-hand derivative. So that's as h shrinks towards 0, but from the left. So this would be forming a little secant line with something just to the left of the number. Okay, so again, say we were looking at a equals 3. This would be forming a little secant line from 2.9 to 3, 2.99 to 3. So looking to see what the derivative is approaching as you come in from the left, or looking to see what the derivative does as you come in from the right. So for example 4, we're going to show one example here. So we want to talk about a left-hand derivative and a right-hand derivative, but no overall derivative. So as we come in from the left, we're going to be looking at this piece right here, to the left of 0. It's like negative 0.1, negative 0.01, and then this is the function we're going to check as we come in from the right. So as we go from the left, we're going to use that x squared function. So we're taking the limit as h approaches 0 from the left, and then we can plug in. Let's go just... Well, that last video cut me off for some reason, and of course I kept writing and I kept talking because I didn't know that the recording had stopped. So I have everything all written out. I'm not sure exactly where I stopped talking along here. I know I had a little bit going on with the left, but this is a very similar idea to taking a left-hand limit of a function and taking a right-hand limit of a function. So I was kind of drawing this picture in as we were going. So here's the piecewise function that we're looking at. It takes on the shape of the parabola x squared over to the left, so that's this half right here, and then it takes on the line 2x over to the right. So those are the two pieces. And so the left-hand limit, you're still doing this exact same limit derivative, just like this, or like this. Either you're coming in from the left, though, or you're coming in from the right. And so as you're coming in from the left, we still want it to do 0, and so we're looking at the point x equals 0. So we go from 0 plus h to 0, plug everything in like this. So careful here, this 0 and this 0 are different. The reason we're using a 0 here is because x is approaching 0 from the left. We're using 0 here because h is always approaching 0. So we plug this in, we've got 0 plus h squared, which of course is just an h squared, minus 0 still leaves us with an h squared. I forgot my limit clause right here, so I tried to sneak it in. This h in the denominator, h squared over h gives me h. And so with this just left as an h, as h approaches 0, I can just plug my 0 in and I get 0. So if you're looking at the picture, what this is showing is that as I move towards 0, as I'm coming in from the left, the slope of this parabola is approaching 0, which you can see. I mean, we've got kind of a steepish negative slope, and then it gets less steep and less steep until the slope is 0. And that's what happens at the very bottom of the parabola. But then from that point on, it takes on a new shape. And so as you're coming in from the right, you plug 0 plus h and 0 into my function 2x. And so here you plug in the 0 plus h minus what we get when we plug in 0. So this whole numerator just simplifies to a 2h, because of course the 0 doesn't do anything, and 0 plus h is just h. So we've got 2h over h. The h over h will reduce down to just 2, and then this is like that limit rule where we know if this is just a constant, then it's just a horizontal line, and so as h approaches anything, the value would just be 2. So what that's saying is that this right-hand piece has a slope of 2 as x approaches 0, which we know it's a linear function. We know it has a slope of 2 the entire time. So constant slope of 2 from the right, approaching a slope of 0 from the left, what we'd say is actually very similar to the limit as, like a left-hand limit not equaling a right-hand limit. Since the left-hand derivative doesn't equal the right-hand derivative, we say that the function doesn't have a derivative at x equals 0. Or what we're going to talk about in the next couple of days, we'd say that f is not differentiable at x equals 0.